So good morning, everybody. I'm forcing myself to say morning rather than afternoon or evening when I normally give these sorts of talks. So yes, as you've heard, this is a talk about one particular telescope because I figured that telling you about all the telescopes and all the work they're doing and what we're learning about the universe was just far too much for 1 hour. I think it's probably too much even for an entire series of lectures. So this is a talk about one particular telescope, and I'll tell you about this telescope and how it fits in with others. It's got the rather awkward name of the Large Synoptic Survey Telescope, and it goes by the initials of LSST. And LSST is also the initials of what it's doing, which is a legacy survey of space and time. And I'll say why it's got that particular name shortly. So the LSST is sort of interchangeable between, are we talking about the telescope or are we talking about the work that it's doing? So I'm just going to be referring to LSST, and I'll say something on the very last slide about the use of that particular acronym. So I'm going to be talking about why it is that there are such things as telescopes that survey the sky. You're probably familiar with other telescopes like the Hubble Space Telescope or the recently launched James Webb Space Telescope, but this is talking about a telescope that is surveying the sky. So the question is, why do we need sky surveys? I'll be talking about the LSST. Why are we building another telescope? Why is this in the process of being built? Can't we just use whatever telescopes happen to be lying around? There are many dozens of them around the world. So why don't we just use one of those? I'll be saying a little bit about the science that we hope to learn from this telescope, and I'll also be talking about the technology that will be put together or has been put together to deliver that science. And then I'll say something right at the end about how they're going to, the strategy of how they're going to survey the sky and what they're going to do with the data. So the question is, what's out there? That's, of course, a lot of what astronomy is trying to answer. It's a pretty fundamental question. What is out there in the universe? And you might assume that, well, surely that's what all the telescopes in the world are trying to answer. Well, yes, but no, in the sense that most telescopes actually are looking not to try and find out what's out there. They're looking at very specific objects which have already been found, have already been surveyed, have already been catalogued. In other words, the Hubble Space Telescope or the James Webb doesn't just randomly look in the sky and hope to find something interesting. It's already got a to-do list of all the interesting objects that are out there that are worth investigating in more detail. How have we found those objects? By surveying the sky to see what's out there. And there have been a number of sky surveys over the last century or so. If we go back far enough, back to the middle of last century, at Palomar Observatory, they decided to do a sky survey because they thought it was important that they photographed effectively the entire sky that could be seen from that particular observatory. So they used a large camera. There's a pencil drawing of it. You can get an idea of the scale from the little gentleman here who's sitting at one of the guide telescopes. 48-inch mirror, that was used to take a total of 2,000 photographic plates. These are large photographic plates, about 12 inches on a side, which contained a huge amount of information at the time on these emulsions. But they were just photographic emulsions. They had limited sensitivity, so there's a limit to the faintest object that could be found. That survey was carried out again a few decades later using more sensitive photographic plates. So back in the 80s and 90s, the second of the Palomar surveys was carried out. But after that, of course, no surprise, we changed from using photographic plates to using CCD cameras, to charge coupled device cameras, digital photography. So there was a survey called the Sloan Digital Survey. It was carried out with dedicated telescopes using CCD images rather than a set of photographic plates. And something like 1 million images were taken, again trying to cover the entire sky as seen from, in this case, the northern hemisphere. That was followed a few years later. It actually overlapped in terms of dates by a survey called PanSTARRS, a bit of an odd acronym, but it stands for Panoramic Survey Telescope and Rapid Response System. You think they might have invented the acronym and then worked backwards to try and make something that looked really cool like PanSTARRS. So that was operating in the early part of the last decade or so. And what I'm talking about is the next in the family of surveys. In each case, The survey is finding more objects because essentially technology moves on, and therefore it's possible to effectively probe further out into the universe to see fainter and smaller objects. So we always need more surveys. So this new one, with this rather mouthful of a name, the Large Synoptic Survey Telescope. Large because it's got a large mirror, synoptic because it's trying to cover everything, in the sense that it's not dedicated to looking for one particular phenomena. Notice the date here, it says 2022 to 2023. It's a 10-year project. It's been designed and built over the last few years. It was supposed to be operational in 2022. No surprise, COVID has put it back a little bit because the construction and testing of various components were delayed in the last couple of years. So perhaps 2023, this telescope might be operational, or at least going through its final testing phase and first light. So why do we need another sky survey? If we've already got sky surveys, why do we need another one? Well, we can judge that by looking at how many objects do we hope to find in this survey. If we photograph the entire sky that can be seen from a particular location, how many stars and how many galaxies might we collect in that survey? And here you can see, as a function of time, the original Palomar survey is back here in the 1980s. Well, the very original one is the 1940s, but we're going to see the first Palomar survey come in from the 1990s, coming up to the LSST. But this is 100 million objects, 1 billion objects, 10 billion objects, 30 billion objects. How many stars and galaxies might we hope ever to catalogue? Well, there's no absolute limit, but that grey line at the top there is an indication of not necessarily a ceiling, but it's a sort of milestone, if you like, because there are hundreds of billions of stars in the Milky Way. We can't necessarily catalogue them all, but there are hundreds of billions of stars in the Milky Way, and to the best of our knowledge, there are many hundreds of billions of galaxies in the observable universe. So in other words, that grey line is a sort of a yardstick, if you like, that we can go by. Not necessarily a limit, but we would certainly like to be up there somewhere. The second Palomar survey, the one with the more sensitive photographic plates in the 1980s and 90s, captured quite a few million objects. The Sloan digital survey, a few years later, captured more. Pan-STARRS overlaps in time, but with slightly better technology, was able to catalogue some 3 billion objects. But the LSST, it is hoped, will be up there in the top right-hand corner. Once it's operational, once it's collecting its information, it is hoped that it won't necessarily hit the grey line, but it will be looking at a rather substantial fraction of all the stars in the Milky Way galaxy and all of the galaxies in the observable universe. Certainly not 100% of them, but a very large fraction. So work on the LSST was started some decade or so ago. As soon as Pan-STARRS and the other surveys stopped, working on this new survey started, and we are somewhere around the red arrow, just before the point at which the LSST is going to become operational. Now, when it comes to designing a survey telescope, there are certain things that are rather necessary. You can't just pick up any old telescope and say, we're going to survey the sky with this telescope here. There are certain characteristics that are necessary, and these characteristics are, it's got to be wide, fast, and deep, meaning it's got to cover a reasonable chunk of sky. If we had a telescope that was quite sensitive but only could image a tiny patch of sky, then we would need to take lots and lots and lots and lots of images in order to cover everything that we want to see in the sky. So ideally, a survey telescope should be a wider field of view than most other telescopes. Fast is used in the photographic sense. I'm not sure how many here are photographers or know about photography, but I'll explain what I mean by fast optics in just a second. Fast optics means the optics have got a large enough aperture for a given focal length so that we can keep the exposures nice and short. Because again, we don't want to survey the sky with exposures that are so long, it's going to take us 100 years to survey everything that we want to see. And deep means deep in the astronomical sense of seeing very faint objects. Very distant objects, very faint objects. The deeper we go, the fainter the objects we see, the more of the universe we manage to catch. So ideally, we want a survey telescope which is good at all of those. It must be wide angle, it must be optically fast, and it must go deep to see faint objects. You can do a little bit of horse trading between the three of those, but ideally you want a telescope that excels in each of those three categories. And just again to cover, for those that haven't met this term before, when we talk about optically fast, when we talk about a fast camera lens, or we talk about a fast telescope, what we're talking about is this ratio of the focal length to the diameter, the so-called F number. So a large F number means a large focal length relative to its diameter, or if you like, a small diameter relative to its focal length. So a lens or a mirror which is catching light with a low F number has got a relatively large diameter compared to its focal length, and that means the image is brighter. So that's all you need to remember about these F numbers. Small numbers mean large aperture for a given focal length, which means brighter. And if it's brighter, that means you can take a shorter exposure, which means you can get more images in one night's observations. So fast means you can use a fast shutter speed because the system is catching lots of light, a large aperture. And if we just take a hypothetical situation, what if we had a hypothetical situation in which we wanted to do a 1-minute exposure with an optical system with an F number of 2, a focal length of twice the size of the lens or the mirror? Well, if we had a different F number, remember a large F number means a smaller aperture for a given focal length, we would need to use a much longer exposure. So where do typical photographic lenses and telescopes that you might have heard of come on this scale? Well, if you've got a camera lens, let's say a wide-angle lens, and you're interested in photographing a nice large chunk of the Milky Way, for instance, then you might use a camera lens which has got an F number which might be F2, F2.8, F4, something like that. Remember, that means the lens at the front is 1/2 of the focal length of the lens. So that might be quite typical. But what about telescopes? Well, I'm sure you've heard of this one, the Hubble Space Telescope. It's got a mirror diameter of 2.4 meters. That sounds very impressive, but its focal length is absolutely huge. Its focal length is 57 meters. And therefore, when you divide the focal length by the diameter, you find that you don't get a really fast result. You actually get a surprisingly slow result. F22, the size of the mirror compared to its focal length, is actually quite tiny. It's only F22. It's like taking a camera lens and reducing the aperture size all the way down to minimum. That's what the Hubble Space Telescope is. And then you say, right, okay, but there are big telescopes on Earth. I know putting a telescope in space is tricky, but there are huge telescopes on Earth. For instance, being built at the moment, the European Extremely Large Telescope. The name is a bit of a giveaway, yeah? Its diameter of mirror is 40 meters, absolutely huge compared to, for instance, the size of this room. So you think, surely that must be fast because it's collecting so much light over a mirror diameter of 40 meters. Well, yes, it is collecting an awful lot of light, but what's important in terms of brightness is how much light are you collecting compared to the focal length. It's this F number again that matters. So what's the focal length of this particular telescope? Well, it could be anything up to 750 meters. For those of you who are used to focal lengths of a few centimeters or a few inches in the photographic sense, having a focal length of 750 meters seems absolutely ludicrous. Divide one number by the other, we find that the extremely large telescope comes out at F16. So remember, we want small F numbers to keep the exposure short. So Hubble is fantastic for seeing faint objects, but it needs to take quite long exposures. The famous Hubble Deep Field that looked deeply into the universe was an exposure of about 1 million seconds. It took about 10 days to get that because it's not particularly optically fast. So it's not ideal for a survey telescope. We need something different. We need something at the top of this table, not at the bottom of this table. That's why we need to build a dedicated survey telescope, not just reuse whatever's around. It's been estimated, with its rather slow response here, that if you wanted to use the Hubble Space Telescope and map out an image of essentially the entire sky, it would take about 100 years to do that. So you can see that that's not really feasible. So we want a telescope that fits these criteria. Wide field, optically fast, goes deep to see faint objects. If you used a digital SLR camera, for instance, the sort that you would use for taking a picture of your dog or your family or whatever, then a wide-angle lens will give you wide, but it won't give you deep. It won't be picking up faint objects. Similarly, if you use a digital camera and put a telephoto lens on it, well, you can get quite faint objects, but it doesn't cover a very wide field of view, and neither are probably very optically fast. And we've just seen that the Hubble Space Telescope and the extremely large telescope definitely will go deep, definitely will find very distant objects as long as you expose for long enough. It's not particularly fast in the optical sense, and it's not very wide field. Whereas the LSST has been designed explicitly to cover wide and fast and deep. Hence the mantra of this particular telescope is wide, fast, deep. And that's what it looks like. I didn't think to ask, can we have the lights down just to make it a little clearer? Yes. Yeah. Maybe it's a little easier to, there we go. So that gives you an idea of what the telescope looks like, an artist's impression. Notice the person standing on the gantry there. Gives you an idea of how big this telescope is. An absolutely huge mirror and a camera that I'll come to fairly shortly. And it has to be a fairly squat-looking thing because it's got to move very quickly. It's got to rapidly move from one bit of sky to another, which most telescopes don't usually worry about. Yes? Absolutely, yes, yes, it's all computer controlled, yeah. So, one of the key aspects of this survey, which makes it different from essentially every other survey that's been carried up till now, is that it will image the entire sky that it can see from its location every 3 nights. It's not going to take years or decades to cover the sky. The entire hemisphere that it can see on any given night will be imaged every 3 nights. You can do that providing you have a large enough field of view and providing your exposures are short enough that you can then basically mosaic the entire sky in 3 nights. So during its 10-year mission, during its 10-year project, it will clearly photograph the same object more than once because it will cover the entire sky in 3 nights, and it will keep imaging the sky, basically imaging everything it can every night, mostly clear nights in its location, for its 10-year projected lifetime, which means lots of objects are going to be imaged over and over and over again, and that is deliberate. It's not just a question of, oh, there's a star over there. The question is, if you image that star every few nights, does it change its brightness? Does it change its color? Is this object that we found over there moving through the sky? If you image it over and over again, you don't just end up with a catalogue. In a sense, you end up with a movie of everything in the sky which is there and everything that is changing. And that's one of the key aspects of this particular survey, which makes it different from all other previous surveys. The Palomar survey, for instance, took 10 years just to take one image of everything in the sky. The difference here is it'll do the same thing in 3 nights, and over 10 years, it'll take effectively 1,000 surveys in a sense. So it's not just the number of objects that are going to be surveyed, many tens of billions of stars and billions of galaxies. It's the fact that it will do this over a time scale which will allow astronomers and scientists to start judging how things are changing. And that is one of the key aspects of this particular surveys, and that's really what makes it unique. It will provide effectively data for every other telescope in the world, including the space telescopes like Hubble and James Webb. It'll produce, here's a list of interesting objects. Go and look at this one because this looks really interesting. It'll provide a survey of all the objects, and then scientists can decide these are the ones we should study in more detail. So I haven't got time to talk about all of the scientific aims of the project, but just briefly, what will it be able to do once it started collecting data? Well, effectively, it's going to do an inventory of the solar system. We know about the planets. We know about the bigger asteroids, the ones that hopefully aren't going to hit us. But what's going to happen is it's going to look at essentially every moving object that's out there within the range of the technology that's there. In other words, every night it's probably going to find thousands of moving objects, many of which are going to be asteroids, a handful of which we already know about, but many of which are going to be new because this is the most sensitive instrument that will allow us to get this information. By taking an inventory of everything that's out there in the solar system, It'll allow us to get a bit more information about how our solar system came to be, how it formed in the first place, and that might well help us understand how other solar systems are forming around exoplanets going around other stars. If we want to know whether there's life out there, we need to understand how planets form. And understanding our own solar system is a start to help us understand other solar systems. In addition, it'll be effectively cataloguing stars in the Milky Way. And that will allow us to get a better idea of the structure and the evolution of how our own Milky Way galaxy came to be and why the stars are moving the way they are. And it will do detailed studies of all the stars in the neighborhood. The neighborhood meaning perhaps many thousands of light years away, perhaps not the other side of the Milky Way, which is a long way away. Remember, we are off-center in the Milky Way itself. But it will allow us to get much more data about what's going on with stars fairly close to us. On a slightly larger scale, when we're thinking about galaxies out there in the universe, it will catalogue many of the galaxies. We know that the galaxies are out there. The Hubble Deep Field stared at one very small patch of sky and saw a few thousand galaxies. That tells us that there are a huge number out there. They have not been catalogued. All we've done is take a few patches of sky and say, yep, there are lots of galaxies out there. What the LSST will do will be attempt to catalogue something of order 20 billion galaxies. Not just a few thousand, not just a few million, but some 20 billion. And it will be looking at individual galaxies and galaxies in collision, which is an essential part of how galaxies evolve. So that hopefully will tell us a little more about the evolution of galaxies since the start of the Big Bang, how galaxies came to look the way they do now. There's lots of things we don't understand about the universe. One key thing we don't understand is that the universe is not just full of the ordinary matter that we think we understand. This sort of stuff, the stuff that stars are made of, the stuff that planets are made of, the stuff that nebulae and gas and dust are made of, that is not all there is. There is something else out there which we call dark matter, which we don't really understand its nature, but we know it's there. We can see its influence on the motion of other objects. But we need to understand what dark matter is a little bit better. And so the LSST will use gravitational lensing, the bending of light as light passes by large galaxy clusters, and that will help us understand a little better where dark matter is in the universe and how it's distributed. On another matter which is almost equally confusing, something is making the universe expand faster and faster and faster. So we have known that the universe has been expanding. We've known that for 100 years or so. But what's surprising is that recently we found the expansion of the universe, rather than slowing down as we might expect from gravity putting the brakes on, it seems to be accelerating, and we don't understand that either. So we'd like to understand what it is that's making the universe expand faster and faster and faster. And it will do that by studying not just a few thousand, but perhaps millions of supernovae. Up till now, we've seen over the last 100 years, something like 1,000 supernovae have been observed in the sky. It is thought that this telescope will probably observe that same number, 1,000 or so, every night that it's operating. In other words, we've had 1,000 up to this point in history. Once this is operational, we'll have that number every night for the next 10 years. So an enormous amount of data is going to be gleaned. And supernovae are fantastic ways of judging distance, and therefore it'll tell us about how the universe is behaving. Regarding the Milky Way, it's actually not easy to figure out what the Milky Way is doing, in the sense of you might think it's easy to figure out that, well, we're in a spiral galaxy. Everybody knows that. But it's actually not that easy to figure out when you're inside it. If you were outside it taking a picture, like taking a picture of the Andromeda galaxy, you can see it's a spiral galaxy. It's not so easy from the inside. Herschel, for instance, thought that the entire universe, or the Milky Way, was a group of stars that looked a little like that. Now we've got a better idea of what the structure of the Milky Way is. That's us there at the bottom, by the way, in the so-called Orion spur of one of these spiral arms. We think the spiral arms look like this. We think there's a large bar in the middle of the galaxy, and there's probably a supermassive black hole right at the center. But the LSST will be mapping out billions of stars, some of which are quite local to us and some of which are much more distant, and we'll get a much better idea of whether this picture is right or not by mapping out the positions and motions of the stars, because it's going to be looking at stars not just as a snapshot, but over 10 years, we'll be able to see not only where stars are, but we'll see how stars are moving. It'll be a dynamic picture of the Milky Way. Another spin-off, it's not what the LSST is designed to do, but a spin-off is that because it's going to be staring at billions of stars and measuring their brightness, it will probably pick up a lot of exoplanets purely by accident, not because that's what it's looking for, but just because if it's measuring star brightness, every once in a while, a planet is going to go in front of a star and dim its light slightly, and we're going to see a change in the star brightness. And if you're staring at billions of stars, even though it's not a very likely event, if you're staring at billions of them, you will pick up a few exoplanets along the way. If one of these stars happens to be not in our galaxy, but in a neighboring galaxy, it could well be that this would be the first observation of a planet in another galaxy. And whatever it finds, it will feed that information to other telescopes so that they can go and look at more detail. If there's something interesting happen, because it looks like there's an exoplanet system around that star, other telescopes will then go and look in more detail to see what they can learn. Maybe the Hubble, maybe the James Webb, maybe other ground-based telescopes would then follow up the observations found in this sort of survey. When looking at galaxies, in some cases, galaxies appear to be entirely separated. In other cases, snapshots of galaxies, like an image here from the Space Telescope, indicate that galaxies are in collision. And it looks like colliding galaxies are much more common than we thought. It is, in fact, an essential part of the evolution of galaxies that they collide with others. And generally speaking, big galaxies eat small galaxies. They're cannibals, basically, and over billions of years, they will change because of interactions. But it wasn't so obvious when we looked at individual galaxies that they have interacted as well. You look at this particular galaxy, known by the name of Messier 63, you look at that and you say, well, it looks like a spiral galaxy, much the same as any other, but can we actually tell whether or not this galaxy has interacted with any others in its past? When we look at individual galaxies, we may say that looks very serene and there's no sign of interaction. But the more we look, the more we realize, well, actually, there are hints of interactions there. If I take that color image and take the color away, and then to make it a little bit easier to see it, swap black and white the other way around, and then if I exaggerate the contrast a little more, you can see, as well as the galaxy, we've got these big swirls, these big tails, which signs of stars that have been ripped out of the galaxy, or possibly ripped out of another galaxy which has passed by. There's definitely been some gravitational interaction in the past that's produced these swirls of gas and other stars in this environment of the galaxy. So although it looks isolated, it has in fact been interacting, and we see that all the time. A very bright galaxy seen edge on, but if I do the same trick and turn it around and bump the contrast up, you can see that there are stars and there are gas and there are dust in huge tails, sometimes larger than the galaxies themselves, that indicate one galaxy has come fairly close to another galaxy, and the gravitational tug of war has actually pulled some of those stars out of the galaxy. So the more we study, and as long as we pick up the fainter stuff as well, which you can do as long as you've got a survey telescope which is wide and fast and deep, it'll pick up the faint stuff, not just tell you there's a galaxy there, fine, but also tell you about all of these other interactions that have been taking place. So again, a huge amount of science can come out of images like that. What's it going to do about dark matter? Well, we don't know what dark matter is, and it's going to be rather tricky to find it. We don't actually know whether dark matter, which is indicated in this artist's impression, because we can't photograph dark matter because it's essentially invisible, but these little dark splodges here are supposed to be indicative of, is that where the dark matter might be? If we look at a galaxy like the Andromeda galaxy, is it possible that the Andromeda galaxy is full of matter and is full of dark matter which is perhaps in splodges, or is it actually uniformly spread throughout the galaxy? LSST via means that is, I'm not going to go into in any detail, but the LSST will be able to look at the sky and judge through this idea of light being bent as it passes massive objects. It will be able to tell where the dark matter is distributed in the universe. And it will give us an idea as to whether dark matter is smoothly spread everywhere or whether it's very clumpy, because at the moment we really don't known. So I've said a little bit about some of the science that LSST will deliver. It'll help our understanding, and it'll give us a list of targets for other telescopes to go and chase. How is it going to deliver that science? Well, it'll need a unique design of telescope. You can't just take a telescope off the shelf and say that will do as a survey telescope. We know the parameters. It's got to be wide field, and it's got to be fast, and it's got to go deep. So that needs essentially a unique optical design. And it will need the world's largest camera, the largest CCD, charge coupled device camera, the largest digital camera, if you like. And of course, if you're going to have a fantastic telescope, you need a fantastic place to put it. With all due respect, there's no point in building a telescope like that and then siting it in Droitwich. Okay, you've got to put it on the top of a mountain somewhere where you've got really dark skies. And there are various places around the world which are the best places to place telescopes. For instance, we've got Hawaii in the middle of the Pacific, a volcanic island, or another set of volcanic islands, the Canary Islands off the coast of Africa there, or another place is in the high Atacama Desert in Chile. These are all excellent places to put telescopes, and there are already a number of telescopes at each of those observing sites. It was decided many years ago that the LST would be sited in Chile. That was decided to be the best place to put it. So some years ago, they said, right, okay, we're going to put it here on this mountain called Charapochon, as indicated by the tag there. No, that's not it on the mountain over there. This is a picture taken from where the LSST will be sited. And it just so happens the neighboring mountain is quite good as well. So the neighboring mountain already has a telescope on it called Gemini South, and they've decided this particular location is also superb. So there's going to be a number of telescopes not so far away from each other at this particular location in the Andes. So if you want to build a telescope, what's the first thing you do? Well, you flatten the top of a mountain, so you blow it up. And then the second thing you do is you get a load of engineers in who come and look at, oh, I don't like the look of this. Yeah, okay, so they basically make sure that they've got a really solid bedrock on which to build the telescope. Of course, the telescope needs to be absolutely firmly grounded. Yes, it needs to track smoothly across the sky, so you can't have any vibration in the rock. It needs to be absolutely secure, so you need a really good, solid foundation on which to put the telescope. So they're basically just checking out that there are no fractures that will stop them placing the telescope in this location. Then a few years back, they started building it. That again is pre-COVID, and that's the most recent one I could find. It's almost complete. They've still got a little bit of work to do, but essentially the building is complete. That's an artist's impression of what it's going to look like. A little telescope on the side is looking at the sky to double check that there were no clouds, double check that the seeing conditions are exactly what they should be, and if necessary, telling the telescope, don't look on that horizon, it looks a bit dusty over there, look on that horizon instead. It makes sure the telescope is optimized for looking at the sky. Inside, the telescope itself is in this sort of turret structure on one end, and in the other funny-looking bit of the building are various optical laboratories, including when the mirror needs to be recoated every once in a while, glass mirror coated in metal. Every once in a while, perhaps every few years, it'll be taken out and cleaned and recoated in the optical laboratory at the other end of the laboratory there, of the observatory. If you want to cover a very wide angle, again, photographers probably know this, it gets more and more problematic the wider angle you want to cover. It's easy to make a lens that will take a picture. For instance, if I wanted to take a picture of you, then getting a lens to take a picture over that sort of angle is not difficult. But if I wanted a fisheye lens to take a much wider field of view, it's much more difficult to make because light is coming in from all directions. And that is generally true of any optical system. The larger the field of view you want to cover, the more difficult it is to make the optics. So to make a very long focal length, for instance, the Hubble Space Telescope with a focal length of more than 50 meters and a very small field of view, is easier than making a wide angle. So this particular system needed a very special mirror, and they wanted essentially the largest mirror they could get. The largest mirror effectively is what's the largest furnace that you have that will melt the glass that you need to make the mirror. And that gave an upper limit of about 8.5 meters. So they decided that the primary mirror would be 8.4 meters diameter. And its focal length is about 10 meters, not much different. Remember, the focal length of the Hubble is much, 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 much longer than its diameter of mirror, and the same for the ELT. Here, we're talking a mirror diameter and a mirror focal length that are sort of in the same ballpark. It means it has a F number of about 1, okay, 1.2. Remember, photographic lenses might have an F number of 2 or 2.8 or 4. The Hubble has got an F number of 22. This is a lot faster. And faster, remember, means it can take shorter exposures to go just as deep. It's a really weird-looking optical system. This is what it looks like as a sort of artist's impression. Light comes in and hits the main mirror. Then it bounces up and hits a second mirror. Then it comes down and hits a third mirror. And then it goes back up to the camera. One of the really weird things is that mirror number 3 is actually the same piece of glass as mirror number 1. It is one slab of glass that's been ground into 2 different shapes to make 2 different mirrors. It means once you've made it, you don't have to worry about lining the mirrors up because they are locked together in the same piece of glass. And this particular design gives you a very wide-angle field of view. How do you make a mirror like that? Well, you get yourself a furnace, which is about 8 or so, 8.5 meters in diameter, and then you fill it with small glass blocks. You perhaps can't see the individual pieces of glass, but you can see this person has got his hand outstretched and is holding a piece of glass which is sort of about the size of a bag of sugar or something like that. So quite a few thousand pieces of very pure glass are put into the mold, and then you heat it until it melts, and then it adopts the shape that you want. Once you're done, you can start grinding the mirror to a curved shape so it focuses the light the way you want it. But you can save a bit of glass by making that shape approximately right in the first place. In other words, if you take the furnace and spin it while it's melted, then the glass flows and it forms a little bit of a bowl shape. It's not quite the right shape for focusing, and it's not the right shape for mirror 1 and mirror 3, but it does give you a good starting point. It means you have to grind away less glass in order to produce the shape you want. So they spin it, melt it, and then slowly cool it down while still spinning it until it's finally solidified again. And there are cameras looking into the melt, and we can have an idea of what that looks like when the glass goes. There's the glass, and then boom, it melts, and then sinks into this honeycomb structure in the background. Repeat it again, it melts, and then sinks into the honeycomb structure. One more time, it melts, and then sinks into the honeycomb. The honeycomb is there in the back to give you nice, strong, ribbed structures on the back, but to remove some of the weight to give you a very strong, very rigid structure. It's a common way of making glass mirrors. And what you end up with is a slab of glass which is then suitable for being ground into the right shape of a mirror. It is not small. 8.4 meters is difficult to appreciate until you see people sitting on it there looking like a huge birthday cake. And you can see some of the honeycomb structure where you're looking through the glass at the back of the mirror effectively. And now that needs to go to a grinding machine to grind it into the right shape for mirror 1 and mirror 3. If you do that, you end up with an optical system which is capable of imaging quite a large chunk of sky. But there's no point in doing that and imaging a large chunk of sky unless you can catch it. What's the point of generating a huge image if your camera is absolutely tiny and your sensor is absolutely tiny? For instance, the chip, the actual detector in the Hubble Space Telescope, is about 4 centimeters in size. You can just about see it there, okay? So it's 4 centimeters by 4 centimeters, 40 by 40 millimeter. That is the size of the chip in the camera, the highest resolution camera in the Hubble Space Telescope. If you generated an image which is much, much, much wider, it would be crazy to only capture a tiny part of that image in a small detector. So they've done things differently. No, that's not it. Just for scale, this is to remind you that the camera that you have in your phone is tiny. So there we see a camera system, entire system, a lens, and behind it a CCD chip, and you can see that it comfortably fits on the tip of your finger. And just for scale, let me put beside it what I've just shown you, the Hubble Space Telescope detector. 16 megapixels, in other words, 4,000 pixels by 4,000 pixels, giving you 16 million pixels in all on a chip that's 40 millimeters across. Substantially larger than the sort of chip you get in your mobile phone. That's one of the reasons that the Hubble gives better images than your phone does. Okay, there's lots of other reasons, like it's in space, for instance, but one of the big reasons is that it has a big image collecting detector. What are they doing for the LSST? Well, just to give you an idea of scale, let's start with the Hubble chip. There's the Hubble chip, which has got 16 million pixels on it. Let's imagine taking that chip and adding a whole load of neighbors. In other words, 8 identical neighbors into a package. And let's think about taking that package and adding another 8. And then let's take that and add another 12. And then add a little bit of other stuff which is required for making sure the telescope is pointing in the right direction. So each of these little colored squares has a different job. Some are for producing an image, some are for guiding. But what you end up with is a detector which, instead of being that size in real life, is this size in real life. That is a one-to-one mock-up of the detector that is in the camera of the LSST. There's the Hubble, there's the LSST, with effectively the same density of pixels. In other words, 16 million pixels in this one, 3 billion pixels in this detector. So it's a detector that is about 0.6 meters on a side, 3 billion, actually about 3.2 billion pixels, and all of that information is read out in 2 seconds to the computer system after the image has been taken. Now, of course, it's impossible for me to show you, even as a simulation, of what sort of images it could produce. My laptop doesn't have a screen with 3 billion pixels on it. This projector, good though it is, good old Epson, this projector is not capable of showing you 3 billion pixels. So I can't show you an image of what you can expect to get from this particular chip. All I can do is to give you an impression by saying, let's imagine we took a tiny bit. Let's just imagine we took that little black square there, a tiny bit of one of the original Hubble-sized chips. What might we see if we pointed this LSST at the sky and took a 15-second exposure? Maybe it would be something like that. Maybe thousands of stars and probably quite a few hundred galaxies if we just pointed at a random point in space. And this is what you would expect, not in a 10-hour exposure, not in a 10-day exposure. This is what you'd expect to get in 15 seconds. Fast, wide, and deep. It's wide angle. We're looking at a tiny part of the whole image. Only 0.03% of the whole image is shown here. But it's fast, optically fast, and we can go deep even in a very short exposure. So if you imagine that's what we would see in the little black square, but the actual image it produces is some, 3,000 times larger than that. So you can see that a single image is going to produce an absolutely huge amount of data simply from the number of pixels that are being imaged. To give you an idea of how much sky is covered, there's the full moon, which is about ½ a degree in the sky. You can just about cover the full moon. Well, you should easily cover the full moon with your thumb at arm's length. That little red rectangle there is the field of view of the Hubble Space Telescope. So when you see the pillars of creation, or when you see the Hubble Deep Field, bear in mind it's only a tiny fraction of the area of the full moon as seen on the sky. By comparison, what's the area covered by the Large Synoptic Survey Telescope? Well, this particular image isn't big enough for me to show you. All I can show you is there's the edge of it. Okay, you can see that circle is the field of view covered by the LSST. Thousands upon thousands of times larger area than the Hubble, which is why the Hubble as a survey instrument would take centuries, but the LSST can cover the sky in a few nights. It's going to be using different colored filters to make sure it gets color information as well as how bright and where in the sky are these objects. That's a reminder of where the visible spectrum is, from about 400 to 700 nanometers. And various filters will be available. working from the ultraviolet through the visible and a few infrared filters as well. A sort of range that's not that dissimilar to the Hubble. The Hubble also works in the ultraviolet and the visible and the near infrared. The James Webb Space Telescope is working much further into the infrared, but this is the sort of range that the Hubble Space Telescope occupies as well. Yes, they are physical filters, and if you want to know what the physical filter looks like, that's what they look like. The camera, you can see from the size here, is pretty huge, and the filters are literally pieces of glass which go in front of the sensor. So there's a mechanical system to move whichever filter you want in front of the detector. So the filters are circles which are a little bit bigger than the detector itself, and will simply move into place to cover the entire thing, and then one 15-second exposure is taken. They won't change the filters that often. It takes a few seconds for the filters to move in position. So they will take different chunks of sky with one filter, and then after a while, change to another filter, and then probably re-image similar chunks of sky again to try and maximize the amount of time they're imaging and minimize the amount of downtime. They haven't got a precise idea of what they're going to image, but they do have a plan. They do have a strategy. This is in the southern hemisphere, remember, in Chile, so they are not going to be able to image the very north. This is the whole sky unwrapped, so you can see the northern hemisphere up here and the southern hemisphere down here. The color coding is how often are we going to image that particular patch of sky. And you can see that most of the southern hemisphere is going to be imaged in the blue, which means each bit of sky is going to be imaged many hundreds, perhaps up to 1,000 times over the project. So we're going to see how things vary, how things move over thousands of data points. There are some regions which aren't going to be imaged quite as much in the green, perhaps only 300 times during the project. And there are some parts, perhaps you can see them, that are dark blue. There might be certain regions or certain objects or certain parts of the, for instance, the Large Magellanic Clouds that are worth visiting more than once, or more than once in terms of the average. And so these will be dark blue. Instead of imaging those perhaps 1,000 times, it might be that those are imaged 2,000 times during the project. There will be priorities for it's worth going there more often than it's worth going there. So most places will get many, many hundreds of visits. Some objects in the sky might get a few thousand visits. Of course, that means an awful lot of data is going to be generated. The technical word is shed loads, okay? It's going to be generating shed loads of data. Just a reminder of where we start from with how much you can store. Do people remember these things? Yeah? Okay, a floppy disk is a useful unit of storage because it contains about a megabyte. 1 million bytes of information can be stored on a floppy disk. These days, barely enough for a digital photo, for instance. So, for instance, here's a picture of zebra. I bet you thought a talk on telescopes was not going to include zebra. Is that right? So a picture I took on Safari, this particular image is about 2 megapixels, and on the disk it uses about half a megabyte of storage. So roughly speaking, megapixels equates to megabytes, very, very roughly. So if you wanted to, you could store one image on a floppy disk. And if you wanted to store lots of images, one option is to switch from floppy disks to DVDs. DVDs store gigabytes of information. 1 gigabyte is 1,000 megabytes. So instead of storing just one image, we can now store thousands of images on a DVD. Basically, an entire enjoyable 2 weeks on Safari can be stored on a DVD. So great for personal use, but would they be any use for storing information from the LSST? How quickly would the LSST fill up disks if we decided to use disks and gigabytes of information per disk? How long would it take before we found that the archive of hundreds and hundreds and hundreds of these disks was full? You might say, well, it probably wouldn't take many months for it to fill that much information. Actually, it would take about half an hour to fill that many DVDs. We have to think of something a little more efficient. So what about a terabyte disk? A terabyte is 1,000 gigabytes. A gigabyte is 1,000 megabytes. So now we're talking 1 million floppy disks at a go. So terabyte disk would probably be more sensible. 1 terabyte, perhaps 250 DVDs. So what's going to happen is you're going to need at least about 20 terabyte disks every night. So one night's observations, because it can take an image every 15 seconds, and it will be taking data essentially all night, it's thought that it would fill somewhere between 15 and 20 terabyte disks every night. Then you say, well, it's clear most nights, so it's going to be clear for at least 300 nights of the year, and it's going to run for 10 years. And we're going to need to store a little bit of technical data as well. As well as the images, we're going to need to store dark frames and flat frames and calibration frames and other technical data. So it's been estimated that the project is going to require 500,000 terabytes. So this is going to be, well, it's an awful lot of disks. Maybe technology will move on. They won't necessarily be using these little things that are 1 terabyte each. They will almost certainly be using larger disks. Maybe in the fullness of time, they will change to using the latest solid-state drives, but that's still going to be expensive if you need 500,000 of them. Even if they are only a few pounds each, that's still an awful lot of money required for data. And then somebody asked, yeah, are they going to back it up? Are they going to copy it? Is the cloud big enough to back up something that big? So an awful lot of data is required. And this is how it's going to work, hopefully. Every 30 seconds, it's going to take 2 images. It's going to take 15-second image, and then almost directly after that, it's going to take another 15-second image of the same patch of sky with the same filter. The idea being, let's check, A, for any defects. Do the 2 look the same, or does one look horrible or out of focus or something like that? And also, has anything moved in those 15 seconds? Is anything so close to Earth, moving so rapidly, like an asteroid going to hit us within the next month or so? Is it possible that anything so close to Earth might visibly move between 2 images taken 15 seconds apart? So they'll always take 2 images as a double check of, for instance, there will always be a little bit of background radiation that makes one of the pixels light up in one that you don't see in the other. You can reject artifacts, in other words. So they'll take 2 images, which adds up to about 15 gigabytes of data every 30 seconds. And then they are going to squirt that down a local network, an intranet, using an optical fiber at 100 gigabits per second. Yes, not megabits, 100 gigabits per second. They'll squirt that down from the telescope on the mountain to the base site at the base of the mountain, which is effectively the headquarters of the telescope. Having got it there in approximately 1 second, they will then send it from South America to North America. And that will take 4 seconds to get something halfway across the world from South America, Chile, to the National Center for Supercomputer Applications in Urbana-Champaign, which is in the USA. They'll use the internet for that. So that's an intranet, a dedicated optical fiber link as part of the observatory's network. But this is the internet. How do you get 40 gigabits per second on the internet? I would hazard a guess, most of you haven't got that at home. Even if you've got fiber to your door, you're probably getting maybe hundreds of megabits per second if you're lucky, and you pay the earth for that. So how on earth do you get information from South America to North America at the rate of 40 gigabits per second? So why is your fiber slower than theirs? Well, your fiber is slower than theirs probably because YouTube is full of cat videos, and that just tends to clog the internet with all sorts of stuff which you're possibly not interested in, but the internet is full of what I might call garbage or rubbish or adverts or all sorts of things. If you have a cat filter on your internet connection so that you don't have to worry about the world and his dog and his cat sending and posting social media feeds, then you can get information from South America to North America at the rate of a few seconds to shift 15 gigabytes. That means that you can put the data from the telescope onto a supercomputer within about 5 seconds. And the supercomputers already exist in North America. It wasn't considered worth building a supercomputer center in South America. It was considered more sensible to send it over a few seconds to a supercomputer that already existed. So it will arrive here, and then they will do some very fancy number crunching. They will do the obvious thing of compare these 2 images and see if there's any artifacts. but they'll also compare this chunk of sky with what the chunk of sky looked like earlier that night, or the previous night, or 2 nights ago. Whenever that image was last taken, they'll compare to see if anything has changed. Has any object moved? Has any object changed its brightness? Has any object changed its shape? Has any object changed its color? Anything that is different between this image and the last time that sky was looked at is called an event. Something has changed. And it's estimated that there will be 10 million per night. If you wish, you can sign up for a text. If you're interested in, tell me when something has changed, you can, if you wish, ask them to send you a text. But you'll get 10 million texts per night. The idea is that scientists will sign up for a particular set of those events. Tell me when there's a new supernova. Tell me when there's an asteroid that's moved by at least that much. Tell me when any star has changed its color by at least this much. So scientists that are interested in particular aspects of the data will sign up to be told at effectively a few minutes' notice when something interesting has happened in the sky. And also it will be automated to the point that these events will be fed to other telescopes. So if a telescope is sitting somewhere in the world and is told a supernova has just gone off, then within a few seconds it can point and have a look at what's going on with that particular supernova. As well as generating these events of what's different, it will also slowly build up a catalogue. And that catalogue will start after a few nights, and then it will get more and more stars, because as you build up more and more data, and as you revisit different patches of the sky, you will be able to get deeper and deeper and deeper, looking at fainter and fainter and fainter objects. So your catalogue will slowly grow. And it's expected, based on simulations, that the catalogue will end up with something like 20 billion galaxies in it and 17 billion stars. So that's roughly where I placed the LSST logo, if you like, in the top right of that graph of how many objects might we find. We're not quite at the 100 billion level, but we are getting a long way towards that. So these supercomputers will basically crunch, and within 1 minute, the world will know whether or not anything interesting has been found by the LSST. If it's not interesting, it'll get catalogued, it'll put into the survey, put into the list, but interesting stuff will go out within, hopefully, 60 seconds of the telescope actually catching it on the mountaintop. If you wish, you can sign up for an app. I'm not sure the app's ready yet, but the intention was to have an app so that anybody can say, what did they see with the LSST last night? How many supernova did they find? Okay, looks like they found 2,200 supernova last night. Oh, it was a quiet night then. Okay. How many asteroids have they found? How many interesting lensing events of light bending around galaxies have they found? Basically, what's going on? What are the totals today? What does the sky look like? In principle, you should be able to download images, not the entire 3 gigapixels necessarily, but if you were interested in a particular object, you could say, show me what that looks like with the LSST imaging system. So these apps will be available, but the intention is that this is not so much just a publicity stunt. The intention is that serious astronomers will sign up for these events and will be told when interesting things happen. So the LSST is on the horizon. Literally, there are other telescopes in the neighborhood of Chile, but the LSST, the Large Synoptic Survey Telescope, is definitely close. It was hoped that it would be operational by now. It's at least 18 months behind because of COVID, so maybe 2023, maybe it'll stretch to 2024 before this project actually starts, but they are well on the way. And just as an addendum, which is part of the confusion, just pre-COVID, the Large Synoptic Survey Telescope, as it was known up to that point, the observatory in which it sits has now been named the Vera C. Rubin Observatory. That's in recognition of the contributions of Vera Rubin in measuring dark matter many decades ago. So the observatory now has that particular name. The telescope is no longer called the LSST. The telescope has now been renamed the Chamonix Survey Telescope, and that's an acknowledgement of people who've basically put cash on the table. Private donors have made a contribution, so the telescope is named after Chamonix. And they thought it's a bit of a shame because we've been calling it the LSST now for 10 years, and it's no longer the LSST because the telescope has now been renamed. But they thought the LSST as an acronym is so well used over the last 10 years, it'd be nice to keep it. So they decided the survey that I've been describing is going to be called the Legacy Survey of Space and Time, the LSST. Space and time because it's looking at what's out there in space, but it's also looking back in time, just as any telescope looks back in time, and is a time survey because it's looking at the same object over and over again. So it is, in that sense, truly a survey of space and time. So by defining that as the project, they've now got the acronym back again. So lsst.org as a web domain still exists. And so it used to be that it was the website of the telescope. Now it's the website of the project that the telescope will be working on. So I've been telling you about why we have sky surveys in the first place. In particular, why there's a new survey coming online in just a year or so. I've told you a little bit about some of the science questions that the LST will address, and I told you a little bit about the technology of how they are going to be, or how they have built the mirror and the camera that will be integrated very shortly into a working survey system. And then I told you a little bit about what they are going to do with these shed loads of data that are going to be coming off this thing in the next few years. Thank you for listening.